Okay, we're going to get started again here. Yeah. So if you weren't with us before or you came in late last time, all of the materials that we're going through during this tutorial are available on GitHub. So if you go to github.com/statsmaths, both plural, stats, maths. And then the specific repository is useR 2017_NLP. But if you just go to my repository, you'll see it as the last thing that was updated. If you clone that repository, it's completely self-contained. It contains all of these slides, which are in R Markdown, so it contains all the code, all of the data that we're working with, everything you need other than the R packages. So the internet doesn't work great in here, but I can airdrop it to anybody who wants it later, or you can grab it after the talk, or I can write it down for you if you're really having internet troubles. So we're just going to start where we left off last time. So we're in the middle of what we called topic number 2. That was planned, by the way. We planned to sort of end right in the middle of this one, so that's perfect. So just to recap where we are, so we're working with the short stories of Sherlock Holmes. We're going to look at another corpus in just a few minutes, but we're going to keep working through the 56 short stories of Sherlock Holmes. And we have run the SPASI backend using the clean NLP package over this one to not just split out the token. So we have a data frame where each row of the data frame, I can show you here. Let's go back to where it was. So each row of the data frame is a token or a word. So it's a word or punctuation mark in the data set. And then we have all this metadata about those tokens. So we've looked at lemmas, we looked at part of speech codes, and now we're going to go forward and look at the few other things that are on this list and explain sort of what problems they can solve and why they're useful and how we can use them. So I'll let Lauren come in and do the named entity tags.
So we'll move into this. So one of the things that's really exciting is the ability to start finding characters, say places, and other references in our text. And some of them are so common enough, or things that people can seek and are looking for, that they've actually been wrapped up into a specific annotation task called named entity recognition. These are often being added over time. And some of the most common, as I said, are really characters, locations, information about numbers. And we'll look at a little bit of that in our stories again. So here we're just going to filter by the named entity recognition. And actually what we get here in our first story is a few of we can see it identifying them by their entity type, which is great. Sherlock Holmes is a person. Irene Adler is a person. We see cardinal numbers. We also, in ordinals, we see as well, which is not included in this, but what I really like is it can identify locations as well. And this is both helpful. One, let's say we wanted to, again, another way to find our characters in the novel or in our say your main people in whatever text or collection of data or corpus you are working with. But also, I really love the location piece as well. So for example, currently I'm working with about 2,000 oral history interviews from the 1930s that were done among sort of your average person in the United States. The federal government funded these oral histories across the US. And so what we're doing is using named entity recognition to identify all the locations of the people in those oral histories and where they came from and where they traveled. And why this is actually even more interesting in the context of 1930s America is because this is a time of great migration across the United States because of incredible economic change. We can scale that up for more current issues as well, thinking about how people might tell their stories about where they've been or where they are headed, and actually then being able to map people across. We could see demographic shifts. This could be important for areas like medicine, demographics for governments as well, and other areas. So that kind of ability of the NLP pipeline here to actually identify those people or places and actually then use that information to then scale up for one more level of analysis. And so what you can see here is it not only does that, but it can actually distinguish between people and places, as I said. So here we're just going to look at the entity type of people. through here, and we're going to look at the top 10. And we can actually then pull the top 10 people in our story in A Scandal in Bohemia. And we actually start to get a sense of who our main characters are as well. It's not perfect. Briony Lodge is actually a place, but it's really, really close. And it gives us sort of a shorthand way very quickly to look at all the people. So earlier we talked about the ways to do this through tokenization, right? We did all these little tricks to do that, right? And then we looked at other ways. And this, out of the box, starts to be able to do that by identifying the people in the text here. And this is also really possible in part because of dependencies, which we're going to talk about in a minute, where actually behind the NLP pipeline it's mapping the sentence structures, nouns and verbs, and who's the object of what and where. And a part of that as well is a whole set of categories that we can draw from here. Dates, for example, might be really interesting as well, particularly if you're working with temporal information. Percentages, money, you can see this being powerful, particularly if you're interested in like economics or finance as well, right? Being able to identify trends and how percentages and numbers might be shifting. You could see this potentially being powerful if you're trying to track the stock market or other areas, economic growth, pieces like that across your corpus of choice. As I said, particularly of interest to me, again, is these location options. Also mentioned for me, the humanist gets very excited about something like work of art. Can we identify cultural things, cultural pieces of cultural work across, say, an entire corpus? Let's say if I am Sotheby's or a big art auction house, can I track what pieces of art are are being sold more or very popular, or thinking about as a museum, what pieces I might want to acquire if I'm seeing trends in the art world across different people being sold, different artists kind of becoming more prominent, and start to see some specific areas. And these are all, I believe, in active development and being trained and developed as well with SPASI, and as well as Core NLP is doing this as well. So the next part, I believe, is dependency parsing.
So the last annotation that we're going to look at are dependencies. So dependency parsing. So dependencies are links between tokens within a sentence. So they indicate the grammatical relationship between any two words in the sentence, or between two words in the sentence. So one common example are that there's a type of dependency that links an adjective to the noun that it describes, or an adverb to the verb it describes, or a verb to the direct object that it acts on. So dependencies sort of start, you can see that as we're going down this list, the annotation tasks are getting more and more complex. So dependencies are the most complex of all of them. And also, if you time how long each of these takes, dependencies takes the longest of all the things we're looking at. So when you look at all of the dependencies within a sentence, it actually forms a tree-like structure. So if you're familiar with graphs, the graph of all the dependencies is a tree. There are no cycles in it. So I don't know if any of you had to do this, but in middle school I had to actually go to the board and like diagram sentences. So say like this is the root and the noun and the verb and all of that on very simple sentences. So this is essentially algorithmically doing that. So it's deconstructing the way that the sentence, the parts of the sentence interact with one another. So for example, this sentence here, we can almost reconstruct it by looking at it. The sentence is, bills on ports and immigration, so that's the left-hand side, were submitted by Senator Brownback, comma, Republican of Kansas. So it's a really a classic sentence that the Stanford Core NLP people have used for a while to describe all the things that can go well and wrong with the sentence. And we see some examples here, like ports and immigration is a conjunction. We see submitted at the top. There's actually a missing link at the top, which is saying submitted is the root of the sentence. So there's a dependency saying submitted is the main verb of the sentence. And then is another interesting one. Senator Brownback, NN, is saying this is a compound word. So we could have made the compound word piece that we showed before, where we tried to find proper nouns that occurred right after one another. We could do them even more exactly by finding this NN tag and linking words together by the NN dependency. So just as an example of what this looks like in the data set, so let's look at our NLP data set. I'll take just the first document and the first sentence of that first document and just pick up the columns that have to do with dependencies. So this sentence is, remember, it's to Sherlock Holmes, she is always the woman. And so each of these words is related because it's a tree, has an arrow into one other word. And so here we have the relationship and then the source that it is actually related to. So by taking the relation and the word source, we could reconstruct a tree like this for the sentence. So to, for example, is attached to the root. It's the main verb of the sentence. Sherlock Holmes, there's a compound relationship between Sherlock and Holmes. She has a noun-subject relationship to the main verb of the sentence is. So you can reconstruct the sentence and do interesting things with these dependencies. So one way, and we'll actually see in the next deck of slides, dependencies, some of the best applications are on nonfiction text rather than fiction. But I'll show you one example of something we can do with the Sherlock Holmes novels or stories. So if we take those and we filter out just the words that have a noun-subject relationship, so it's a word, a noun attached to a verb, and it's the noun that's doing the action of that verb. And we take just the ones where the part of speech is a proper noun. So I just want to figure out what are the characters doing in the text. And so here, and I'm not tabulating them or summing them, I'm just looking at all the instances where I have a particular, or I'm counting them and I'm throwing out, I'm just finding pairs that occurred more than once. So Holmes in the first novel likes to murmur, he likes to say things. In the second book, he likes to remark and say things. Some of the other characters are just connected to the verb to be, to say, to come, to remark. And so looking at these and tabulating them, especially if we could map all the characters to their age or gender, or whether or not it's like one of the serial characters like Holmes or Watson or one of the characters that only shows up once, we could see kind of the rhetorical differences about what types of language are used corresponding to each character. And there's been some interesting work doing this, particularly with its regards to gender. So people tend to use more passive nouns when they're speaking about women, more active ones when they're speaking about men, which is obviously problematic. And you can see that by getting the dependency relationships and tagging them together. And notice that you can't just do this by figuring out which words are next to one another, because the noun and the verb that noun is the subject of can be separated by many words. So you really need this dependency structure to do that. Okay. So that's the end of the second topic. So we'll move on to the final one here. Modeling textual data. So the final topic, so the first topic, just to reiterate like where we were. So the first topic was we just did tokenization. Tokenization is great because we don't need any fancy backends. But for the most part, although there are some exceptions, Arabic's hard, some of the Asian languages we can actually do pretty well, but there are always going to be some errors doing tokenization with the tokenizer's backend. But we can do pretty well on any language that we want and at least get something that approximates the truth. And using a lot of the tricks that we saw on the first deck of slides, we can figure out who characters are, we can find themes, we can do a lot with those tokens. The second one introduced, well, what happens if we want to use more? We want to figure out get a deeper level of what's going on in that text. Well, we need these more complex backends, but they're very useful. We get part-of-speech codes, we get dependencies, we get entities, and you can see how much more accurate they are and how much more we can do with them. And we're just scratching the surface here. We could go days on end showing you just application after application of all the different ways we could use different types of dependencies and part-of-speech codes and entities. So this final topic, we sort of want to show you how we can take the data frames that we're working with and actually model them. So we can convert them into matrices, we can do predictive models, we can do unsupervised models, we can do things with them other than just this exploratory analysis. Exploratory analysis is fantastic, I think it's really, really important, but there is kind of the farther down the pipeline actual modeling of text, so we wanted to show that as well. We'll also look at a different data set there. Do you want to?
So we're going to move on from Sherlock and move to a new set. But just before we start, just to look here again at some of the packages that we're going to be using, mostly the same. We are going to add topic models as well to our set here, for we'll be doing some topic modeling along the way. So we're actually going to change pace, and we're going to move to the President of the United States State of the Union addresses. We didn't plan for this to be on July 4th, but somehow it seems fitting. And so we're going to look at the speeches of them. So basically, the president has to, I think the technical term is, from time to time, give a speech to a joint session of Congress. And basically what the speech from its beginning talks about where the nation has been and where it is going. And it is often a moment where either a new president sets up their new agenda, or a departing president affirms their agenda, and where their successes and tries to shore up their legacies, right? So it's become a kind of a hallmark speech of U.S. Of U.S. It's a major event. People sit and all watch it, and much commentary occurs afterwards. So what we're going to look at today is we're going to pull in those speeches again. Like last time, we've already annotated them so that you don't have to have SPASI or set up on your machine right now. So you will already have the annotated President State of the Union addresses if you have them, if you want to follow along. So we're not quite done with exploratory analysis. It's always a part of how we approach things, because in part it's really always great because it's a gut check to see if what you're looking at and you pulled in is right. In this case, we know, we've looked at this a million times, that what we've given you is the actual speeches, and they're cleaned and they look good. But often you can be pulling in data, and sometimes you'll want to look for outliers to see if something is wrong with your data. You've picked up something you didn't mean to, something's encoded wrong, whatever that might be. So here, we're going to just look at basically the distribution of sentence lengths in the corpus again to give us a sense or a quick feel for our data. Lo and behold, we're looking pretty good. Our sentence lengths, our median is about 27 tokens. So these are tokens on the bottom. But then we've got this one that's 681. We have an outlier. What in the world is going on here? Well, it turns out one of the presidents was very much into bulleted lists. So it's 681 tokens of a bulleted list of all of their agenda items. I'm sure if they got through one of them, that would have been a successful presidency, right? But they wanted to make sure we knew them all. So there's a few things you can do with that. One is now we know, and we can still do our analysis based on that. Or two, we may decide we want to throw that one out in some way, or we want to treat those bullets like sentences in some way. So we may want to make a decision about how we want to deal with that one outlier. Again, like any of this, we're making decisions along the way, every step of the way. So in our case, I believe we just left it as is for now. So next we can do is just look at the most common nouns in the corpus. Again, luckily, we've had this great part of speech tagging, so we can just pull up the nouns that we want to look at. We're just looking at the top 40. They've been limitized as well. So we can deal with something like they gave acts, or they have one act, right? Citizens versus citizen, those kind of terms. A good gut check, again, to say, do these words make sense? Yeah, program, citizen, state, treaty, the kind of language that one would expect to see in a State of the Union address. And also just gives a little bit of a peek right off the top about the main topics and ways that presidents are framing the nation. And we might imagine if we looked at other countries, this might look different, right? This could be an interesting comparative look to see how different countries, different leaders, different companies, if let's say we took all the media of a different company and looked at how they framed themselves versus someone else, right? A different company, these kind of things, these rhetorical analyses. So how long is each State of the Union in words? And so do they differ based on whether they were written or given as a speech? So they've gone back and forth over time about whether they were offered just as a document over to Congress or given orally. So we can actually we can take a look at them based on that, we're going to, again, to do a left join of that metadata so that we know who gave the speech, what year they gave it, and those are the two main metadata components, and there's just a naming for it. So we'll pull those in to give them their ID, and we'll plot them. And what we can see here is that early on, they were given as speeches, then they became written, and then throughout the kind of early 20th century, they were kind of a blend, and then mostly given as a speech afterwards. And we can see that the speeches are pretty much the same length in words, and then when written, they kind of vary. Some people got very verbose and expected everyone to sit there and read for a long time. So we can see these kind of outliers, and sometimes it's interesting to know which presidents did that, why they did that, well, why they might have felt the need to do this. I believe one of the longest is going to be right around the Vietnam War, right? So there's a lot of you can start to see some trends in where some of the speeches get longer, particularly maybe an indicator, say, of turmoil or a lot of debate within the country, right? May or may not be, but it's something that we may be able to start to see. And so we can see those divides right there just by looking at the length of words. So the next part is document summary. Yeah. So another part we can do is just a high-level summary of the content by just looking at the direct object dependencies. So where the noun is not a very common word. So here's an example using the first address by George Bush. We're just going to pull those, looking at his 2001 speech. So if we look at those, we can see what he's talking about. So increasing layoffs, projecting trillions. And so we can see the relationship between his terms. And we see here a lot of conversations around the economy. We have things about fairness, about internationalism, divided conscience. We see this is a time when he was talking about, I believe, compassionate conservatism was the sort of tagline of the party at that time. So you see that, fight homelessness. This is, but when we actually look a year later, right after 9/11, we see an incredible shift in the rhetoric of the presidency. Many of the sort of policy approaches and ideas about sort of global ideas and approaches toward a global international community switch very quickly and are retracted very quickly. And we see this immediately in the rhetoric that comes out of the State of the Union address and would sort of foreshadow a set of policies moving forward. So we can see things like vigilance. This is around the time of the anthrax scares, and we start to see dependency, safeguards, a lot of language around security and a framing of an international other in sort of in less friendly and compassionate terms. And we can see that by looking at the relationships between the objects of these verbs as they get articulated in the speech. And so we can actually begin to do this throughout any of the text in which we're working with. And we can actually start to see trends in the language across. Just for a little bit of switch, we can actually then look at someone like Woodrow Wilson back right after World War I, and we can start to see different languages about democratization, manifestations, and we can see sort of different, a different language in response to a the post-war landscape then as well. So we can actually start to get a sense very quickly of some of the individual speeches, and then start to look at them by president over time, and by president and then by over time. And you can imagine doing this on a sort of series of corpus of your choice. You want to talk about this? Yes.
Perfect. Yeah, so that document summarization thing works really well. Just to mention one other thing, just with having to do with the document, I was just thinking about this, or didn't forget to say something, is that we can do more, a better version of document summarization by essentially extending this idea to grab the other words that are modifying things in here. So for example, we see produce stagnation. I think he wanted to not produce stagnation, or he was worried about it. So you could find the adjective modifiers of these things and build them out a little bit more and do a really good job of summarizing the documents. So the dependencies, I think, have the biggest potential that has not been fully realized for doing interesting things in statistics. But now I want to switch gears. So we we've had this pattern of we wanted to get to data frames really, really quickly so that we can do everything that we like to do with data frames. We can summarize them and plot them and work with them much as we would any other data set. Obviously, the things we want to do with them are slightly different, but we like data frames. They work so well in R. Now we actually want to switch gears a little bit and turn those data frames into matrices so that we can move on to more the modeling portion of what do we do with this text analysis, right? I'm a statistician. I like to model things. I like to predict things. And I'm going to need to get some sort of a matrix in order to do that in most cases. So conveniently, cleanNLP has a function. And so I've said so far that essentially once we have those data frames, we don't need anything in cleanNLP. Well, I guess we need the word frequency list, but there aren't fancy functions that we really need a lot of. This is the one exception. So there's the get_tf_idf that provides a mechanism for going from the data frame to a matrix. And why is going from a data frame to a matrix difficult, or why do we need a special function for it? So in R, we have the formula interface. We can give data frames to a function like LM or GLM, and we'll have that data frame turned into the data matrix that we need. So in a lot of instances, we don't really need to worry about that conversion. The reason it's harder in text analysis is that the level of analysis, or the unit of analysis in our data frame is a token. But usually when we're building models, the level of analysis is the whole document. I want to predict something about the document, or maybe a paragraph in the document, or a sentence, but not the token itself. So I need a way of summarizing all of the rows about that document and saying something interesting about them as a matrix that has features that I can learn on. So the classic way of doing this, there are some others, but the classic way of doing this that works really well is to construct a document term frequency matrix. So this matrix has one row for every document. So here we have the documents, So this is just an example from another data set. So we have 9,500 documents in this example, and then we have all of the tokens that create the text as columns. And the count that go in the matrix are how many times did that token occur in that document. So in this example, the token I occurred in the first document 20 times. The word commute occurred in the first document 0 times, and so on and so forth. And so this is the type of matrix that summarizes the information that we have in our data frame as a matrix that we may actually want to do predictive modeling and unsupervised modeling on. Note that we don't have to have every single token. So in theory, you could picture this having every token that occurs in the text, but we could only use the tokens that we want. So there might be a lot of rare tokens that only occur once. We don't need them. There might be a lot of, maybe I don't want verbs, maybe I don't want adjectives, maybe I only want to look at lemmas. You can even take this farther and look at like bigrams and trigrams. So this idea is fairly malleable. So in order to get a matrix like that, we take our data frame that we've been working with, our nice State of the Union SOTU_NLP data set. In this case, since I want to look at the themes that are going on rather than the style of the speech, I'm going to filter out just those parts of speech which are non-proper nouns. So I just want the non-proper nouns. I don't want to know what verbs did they use. I just want to care what they're talking about. And then I pass that data set to the get_tf_idf function. And so it has some options that are interesting and useful to use. So it has a min_df and a max_df. So it's the minimum document frequency and the maximum document frequency. And so what this function is going to do fairly efficiently is only include terms that occur in at least 5% of the speeches and at most 95% of the speeches. So why is that important? The 95 is useful just because I don't want words like stop words, essentially. It'll get rid of those stop words. But the 5% is really important because it turns out that if you look at all the unique tokens, most of them are only used once. So there's this like Zipf's law that shows that most that there are going to be like proper names, locations, names of specific bills, specific mountains, like very specific things that aren't interesting because they only happen once or twice. This is going to filter those out. And then the last two arguments there, we're not going to concentrate on them too much, but they just describe the weighting of the matrix. So This matrix here is a raw term frequency matrix. We can weight it differently to sort of make those numbers smaller. If that word occurs a lot over the whole corpus, we can take the logarithm so that 1,000 isn't that much bigger than 100. And there are different weighting schemes. And I'd be happy to talk more about why I might use a certain weighting scheme. There's also a lot of information in the help page of the get TF-IDF function. So we'll just use this one here, which is essentially the default. So what comes back from that matrix is a list with three elements. So the first is a character vector that gives me the vocabulary. So it gives me all of the tokens that have been selected. It tells me what are the columns of this matrix, the TF-IDF matrix. The other one is the set of IDs. So it tells me what are the rows, what are the row names of this matrix. And then the last one is the matrix TF-IDF. And that is the term frequency. In this case, IDF stands for inverse document frequency. So that means I'm weighting these terms based on how many documents did this term occur in. But in your mental picture of it, you can just think of this simple counts version of it. And the dimension of that's that matrix. So it has 236 rows, one for each speech. And then in this instance, we picked out 2,356 nouns. So by doing that filtering, we got rid of the stop words and the really rare words. So what can we do with this matrix? Well, the matrix has only a few hundred rows, and it has thousands of columns. And so one thing that's natural to do with it is to do dimensionality reduction, right? If we want to plot it, I want to understand it, it has too many columns for me to do like scatter plots or something with. So kind of the classic tool in statistics would be to do principal component analysis. So I can use any of the great base R functions that do principal component analysis. I decided to wrap up my own little function in clean NLP that just stops me from going back and forth from a tidy data matrix to a not tidy data matrix. If you don't want to learn about that function, you can just use the ones you're familiar with in base R. So I call the tidy PCA function. I give it the matrix I want to do principal component analysis with. I give it all the metadata that I want to attach to it. So in this case, it's like the president's name, the speech year, the party of the president, etc. And that comes out. By default, it just finds the first two principal components, but I can make it find as many as I'd like. And then you can see here it attaches to each. We just see the first 6 rows here, so these are all George Washington speeches, but it attaches to each speech the first 2 principal components. And why is this nice? Well, it's a way of doing unsupervised learning. So I can see sort of, are there kind of global temporal patterns? Are there party patterns? Like, can I sort of put all of these speeches into some plot that describes what they're talking about? So this is a really simple ggplot that sets up the plot on the next screen. The plot on the next screen is really long because I wanted to make it look pretty, but this will get the point across without looking as pretty. So the plot looks like this. So each speech gets a dot on this plot on the first 2 principal components. And I have labeled the first speech by each president. So you can sort of see this temporal pattern as it moves across. I tried to pick a color scheme that would work well on a projector, but you might see it better on your own computer where you can zoom in. But for the most part, you see that there's a really strong temporal pattern. So Jefferson and George Washington are up here. And then they move down throughout the years, down across this principal component, and then they move back up. And then all the 20th century people are over here. And the 2 different arms are actually separating the speeches from the written speeches from the spoken speeches. So there are some interesting patterns in here. We could kind of zoom in on pieces of it and see if there's anything even more beyond that. But at least this is sort of a gut check that it has interesting patterns that make sense to us and mimic what we know about the speeches.
And the fun part's when you have a real outlier. But so one of the next parts we'll talk about then is topic modeling. So these are a collection of statistical models for describing abstract themes within a textual corpus. Each theme is characterized by a collection of words that commonly co-occur. So here's an example: crops, dairy, tractor, hectare, farming. You might get bank, finance, stock market, or Wall Street, right? These would be all around a banking and the financial industry. So you can start to see themes that come out into a text. So one of the most popular ones, and the one we're going to talk about today, is LDA. And this is a Bayesian model where each topic is described by a probability distribution over a vocabulary of words. And then each document is then characterized by a probability distribution over the available topics. So to fit an LDA on this, we can actually do that in our clean NLP. We can use our clean NLP object and do it with the TF IDF object that we've created, and then run the topic models on top of that. So in this case, we're just going to topic model the nouns because we're mostly interested in some of the major themes in this corpus as well. So as a way to do that, looking at just the nouns. You may have other reasons you want to look at verbs or want to just look at the entire corpus. But in this case, we've decided that nouns are the way to are going to be the most indicative of some of the major themes in this corpus, and it's usually the most often what we do it on as well. And what you'll also see over here is you'll see when you're running LDA, you'll see K equals 16. This is where you can actually pick how many topic models you want to run. This is a little bit of trial and error. You may start with 10, you might then use 50 or 25 and see how it comes out. And the reason people, we often tinker around with this is sometimes you'll say, let's say we ran 50, we might see 2 or 3 topics that look like they really should be 1. And so we'll lower the count as well. So maybe instead of doing 50, we'll do 25 and see. Or if we only do 10, it may not be enough and it doesn't mean much. It's not particularly mean, it's too jumbled up. So it's a little bit of tinkering around and seeing how to approach that. And so what we're going to do here as well is then pull the 5 most important words in each topic. So part of what LDA is doing is it's going to give a weight to every word. So every topic, well, this will make sense in a second, gets a weight within that topic as well. So when we look at this, act, citizen, commerce, object, measure, these are our top 10, top 6, these are our 16 topic models. But every word in the corpus is sort of a long tail off of this, each one of these topics, but it's a lot less meaningful, has a lot less weight to it than the first, say, 5 or 10 words or so, are usually the most dominant, the highest co-occurrence. And so we can then see these words cluster together around major topics in our corpus. So we can see things like gold, silver, cent, condition, about monetary standards. We can then see other topics around dollar, policy, industry, business. So we start to see some of the big topics of these speeches over their 200-year run. And so we get a sort of a snapshot of some of the major issues of the period. And you could do this, do this on a series of your corpus of choice as well. And it's another way to get at some of the top themes in the corpus. So then what we can do is plot it across and over time and see how dominant that theme is or that topic is over time. So we can start to see some shifts as well. So art, citizen, commerce, more earlier years. We can see child, world, family, job. Toward the 2000s, this corresponds pretty well with the sort of debates about social policy in the U.S. that really come into the fold in the 1980s and 1990s, the culture wars as they're called. And there are methods as well for then looking at these topics and then digging back in to figure out which speech corresponds to which topic and how well weighted it is in that over time. So we can say, go back, so that's how you can start to do these timings here. And then we can actually see exactly which speech has which weight on these topics as well. So we can start, again, another way of getting at sort of the larger picture and trends within the corpus, as you can see here.
Okay, so this I think is the most fun model that we have. So just because we get to do some predictive learning, some supervised learning here. So authorship detection. So we want to build a classifier that distinguishes the speeches of 2 different presidents. So I give you George Washington, and I give you Thomas Jefferson, and can we build a classifier that figures out either based on the themes that they're using or the language that they're using, which speech was which? Now, if we were to do that just for the whole speech, you'd say that's really easy, right? We have thousands of words. It's pretty easy to figure out which president it was. So to make it a little bit more difficult on ourselves and to learn a little bit more interesting of a feature set, and this is something that's often done in authorship detection, we're going to split the text into smaller chunks. And we're actually going to go all the way to the smallest chunk that makes much sense in authorship detection, which is we're going to look at each sentence. So think of taking the speeches and ripping them apart so that each sentence is now sort of like a document for us. So we're going to compare old Winky Wink, George Bush here. We're going to figure out, can we figure out the difference between sentences that he said and sentences that Barack Obama said? And we'll look at a few other pairs, but this is the one we'll start with. So the ability to do this sort of pretty seamlessly without a lot of change to our code is something that we wrote into Clean NLP because we recognize, having done a lot of authorship detection, the need to do this kind of analysis where your documents at one level, at some point, the document is the speech. But now our document, the way we're thinking about the document, the way we're thinking about the rows in the term frequency matrix, we now want them to be every sentence. And this actually comes up a lot in natural language processing, and I find it to be something that a lot of tools are not very well built to do. I don't mean that too critical, but it's just like a lot of tools, including this one where we have that ID column. The idea of what a document is fairly static. But actually, when you're doing an analysis of text, the concept of a document is very fluid. So the really good example of that, I think, is with Twitter data. So if we're looking at a long stream of tweets, sometimes I want each tweet to be a document. Sometimes I want every tweet by one user to be a document. And sometimes I want a stream of tweets that were all responses to one particular tweet to be a document. And there are predictive models and unsupervised models. There are lots of reasons that I may want to look at it in all those different dimensions. And so trying to make tools where it doesn't force you to pick one of those options, where you can easily move in between them, I think is a real strength. So what we're going to do here is we're going to take the data set, or so do NLP, join it into our metadata, and pick out just the two presidents we want to look at, so George Bush and Barack Obama. And I'm going to create a new ID, which is pasting together the ID, so the document, the speech, and the SID, which is the ID of the sentence. So my new ID is now what I think of as the document ID. And then as before, we'll filter out just the nouns. So then I call the get TF-IDF function and add an option where I say the document var, it's not the default, it's not ID, it's now this new ID. So although a lot of the work that we've done in Clean NLP, and it does have this fairly static idea of what the ID is, we hope that most of the tools and most of the approaches that we do are flexible enough that you can quickly change what the concept of a document is. So this new matrix now has thousands of rows instead of just 8 as it would if we, 16, if we used the speeches of the two presidents. So now I'll create a data frame that just contains the response variable. So I'll make a response variable that asks whether or not this president was Barack Obama. So Barack Obama will be 1, George Bush will be 0. And then I want to make a training flag. So I want to train on some of my data and test on some of the other data. Now, if I made random training and testing sets, I think of that as kind of cheating. If there's a particular topic that someone's talking about, like Benghazi or Libya or Syria, in some ways that's a little unfair because I might have 3 sentences, one after another, and I have the middle one is in the training set and the 2 outer ones are on the testing set. And it's a little like cheating. I'm not finding the themes that they generally talk about. I'm finding a very particular term they used in this speech at this part. So instead I'm going to make the training and testing sets, and I'm going to put an entire speech either in the training set or the testing set. And it does affect the results quite a bit if you don't do this. So I'm going to make the training set whenever the year is even. So when you see the results, all the even years were what I trained on, all the odd years are what I'm testing on. And then the model that I'll use to do this authorship detection is called the elastic net, or it's a generalization of the lasso, if you've heard of the lasso. So I just wanted to put up what the function is actually solving here. I think I missed a square here. I always miss a square in these equations, but you're minimizing the sum of squared residuals like you would ordinarily squares like a basic regression, but you also are penalizing the size of your regression vector. And not to get too much into the math, because I could spend a lot more time talking about this, adding an L1 penalty makes my regression vector sparse. So it means that the words, so the variables here, remember, it's a term frequency matrix, so the variables are the counts of all the different words that my term frequency matrix found. So the regression vector here is going to put a weight on each of the words. Now, if I just did normal least squares, first of all, I'd get some overfitting, but also it would put a small weight on every word. But it turns out that most words don't distinguish George Bush and Barack Obama. They tend to use the word and, but, because all the stop words, even less common words, they both use them. It's just a small set of words that really distinguish the nature of kind of their policies and what was going on during their tenure. So I want a model that sort of only puts a weight on a small set of words. And that'll be interesting in a second because we can look at those words and actually see not just, oh, this model does a good job, but I can see what that model's doing. So the elastic net, I thought it was useful to put here because it is, I think, the go-to model for doing any kind of predictive modeling of text. The other major area of application of it is in genetics. I mean, there are lots of others, but the other one I think it was originally developed for was to do genetics, where you put in lots of genes and you don't want small weights on each of the genes. You just want to know the few that might are affecting a disease or a treatment type. So you'll see in a second why this choice of model is very important. So now I can call from the GlimNet package, which is a really great fast package for fitting the elastic net. I'll call the cv.glimnet. The cv.glimnet will choose that tuning parameter for me using cross-validation, and I'll fit it just on my training set. And because I'm doing classification, I'll tell it to use a binomial model because my response is 0, 1. And you can just see that I'm using the matrix that came out of the TF-IDF matrix. So it's easy. So if you want to apply really any model, I think some people in the break were asking me, like, well, what other packages can you interface with the output from clean NLP? Well, essentially anything that allows you to give it a matrix when you're doing modeling you could use. So you could use neural networks, you could use support vector machines, you could use any model that accepts a matrix, which is most of them. And then what we'll do is, so that model gets fit, it takes a few seconds to run. Now I'm going to predict on my entire matrix, not just the training set, but on the training and testing sets. I'm going to figure out what's the predicted probabilities of each of those sentences and add them into my data set, my data frame. So those predicted probabilities, just to make the reference really clear, so that is the probability that this sentence was spoken by George Bush, or Barack Obama, probability that it was spoken by Barack Obama. So 1 would mean this is something George Bush would never have said, 0 means the other way around. And so you can see we have a new column here with the predicted probabilities. And this is just a sentence, so if you think of just a one-off sentence, not every sentence is easy to figure out, but on the whole we should be able to predict trends and see that George Bush's sentences look more like him and vice versa. So I think a really nice way to visualize how well this works is with a box plot. So we'll take all of those predicted probabilities, group them by the year, and see for each particular speech how well did we do. And this is nice too because we split the testing and training set by year. So we'll also see whether or not we overfit too much. So this is the resulting box plot. So each line here is a year. And we have, of all the sentences, like what's the distribution of probabilities within that year? So you see, well, the first thing that jumps out at us is that our model makes some sense. So George Bush, his speeches tend to be more to the left. The probability of being George Bush sentences is pushed to the left. And then Barack Obama's the other direction, right? So there's some general pattern here. We see there's a little bit of fitting to the data. So the odd years, the 2008, 2006, 2004, the even years, they're better fit than the odd years. So there's some overfitting to what happened in those particular years, but there is some signal in the others. I think, and then obviously there are some sentences that we're really misclassifying. So down here where it's sort of saying, oh, there's a very high probability that it was Bush, but it's not. There are a lot of sentences, we're bound to get some of them wrong. I think Probably the most interesting thing here, though, and the reason that we keep using George Bush here, because there's an interesting pattern there that Lauren had showed you before, is that in his year, it doesn't actually show up quite as well on the screen here, but the median is all the way on the left side of this bar. So for 2001, that speech actually looks an awful lot like Barack Obama's speeches. So in that first year of his presidency, before 9/11 happened, before this whole rhetorical shift, that speech looks a lot more like Obama's speeches later on. So there really was a huge shift in his last 7 years from the first one. So it's really neat to see that pop out of the model here. And then, as I said, we can use the elastic net. One thing that's really nice about the fact that we use the elastic net is that we can see what the model was actually doing. So I like to print out all the coefficients here, the sign of the coefficients, to figure out which words are positively associated with Bush, which words are positively associated with Barack Obama. And so the sign, any of the words that have a 1 next to them, that was an Obama word, and a negative sign is a Bush word. I don't like to put the actual coefficient because that is too dependent on how frequent that term was in the corpus. There are some ways to normalize them, but I just think looking at the signs is more interesting than looking at the actual coefficient. And a lot of the coefficients make sense. So Bush, as we mentioned, was really interested in foreign policy, war, terrorism. So we see words like terrorist, nation, freedom, enemy, enforcement, regime, liberty, etc. Whereas Obama came into office right in 2008, right as there's the global economic decline, so most of his presidential speeches were about the economy. So you see things like jobs, college, kid, industry, thing, class, etc. Okay. So this is a really interesting technique, so we wanted to show you how it worked when we looked at a few other pairs of presidents, although I think we're going to look at Bush again. So we wanted to compare, we looked at George Bush compared to Barack Obama. Now let's look at George Bush compared to his predecessor, Bill Clinton. I think this was a photo taken from his 1994 State of the Union address. And so the exact same code in here. The probability here is now the probability that a speech was given by Bill Clinton. And again, we see that there's that 2001 was quite the outlier, so it's much closer to Bill Clinton than the other speeches. We see that the Bill Clinton speeches are a little overfit as well to the even years. So they're catching some themes that were specific to those years rather than themes that were actually indicative of his entire presidency. And then we can look at the model coefficients, which in some ways is the most interesting piece of this. And when we were looking at this, we hadn't thought about Bill Clinton in a while. But kind of remembering the rhetoric of his presidency, it was in the 90s, and I think he left, when was it, 2000? Yeah, it was his last year. And so a lot of his, the rhetoric of his was very thinking about the future. So it was in the 90s, it was like, oh, it's the 90s, it's the future, it's 2000, we're looking forward to the millennium. And so you see a lot of words like year and century, and a lot of social programs like welfare and community and children. So very much thinking like forward thinking in those speeches, and then you see a big difference with the words that are more Bush are sort of similar to the ones we saw before. And then just for fun, we wanted to go all the way back because we do have a very long run of presidents. It's one fun thing about the State of the Union corpus. We've really just scratched the surface of it. One thing that's neat about it is that it's a consistent corpus. Like there's a reason that it's constructed this way, but it has over 200 years of speeches, so you can see even the change of English over time. So we can figure out how well could we distinguish George Washington from Bill Clinton. And so when we do that one, you can see the plot looks a lot different. It's much easier to tell George Washington from Bill Clinton. And remember, we just have nouns. You can do a better job if you put in all of the words because you sort of see the these, thys, thine, and all the things that are kind of archaic in English now. But just with the nouns, we sort of see that there are, we can tell much better whether or not something is George Washington or Bill Clinton. The reason that the box plots for Bill Clinton are so narrow there is that the model, when you look at it, looks something like this, so all of the terms are negative. So essentially, it just found words that only George Washington used. And Bill Clinton almost never uses these, so his sentences just get set to the intercept, which is like 0.95. And so the words are things that Bill Clinton wasn't worried about, like tribes and militias and executions. So, which makes a lot of sense. And then you can feel free to play with this. It's actually really fun. It's easy to change the code that's underlying all of these analyses and just pick two presidents and compare them. The only thing you have to be careful about is that it's a little inconsistent about whether or not like the middle name or middle initial or middle name was included. So just make sure you have the right format of it. But you can sort of put any two presidents head to head that you want and see like what's the difference between them. It's pretty interesting. I think we've only done a small set of them, and I haven't found one yet that's not interesting in some way. Do you want to do questions, or should we just do the conclusions? Yeah, I feel like the conclusions may answer some questions. Cool, so we titled this slide, What's Next? To be perfectly honest, I titled it that because, like I said, I like everything to be tidy, and I couldn't think of another word that made this come alphabetically last. But it's a really good slide, so what's next, like looking forward. Conclusions makes it go first, and that really bothers my OCD. So summary of today. So we sort of split this talk into three pieces. I know it was maybe a little awkward since we had 2 breaks and 3 pieces, but like I said, I like to keep everything organized. I think it makes it a little easier, though. I hope you can use these slides and go back and apply what we've been showing you to your own work. And please feel free to email us or come up after, ask questions. We want to sort of have a more dialogue about how this might be useful. But I think that splitting it that way makes it easier to figure out, oh, I remember something from their talk, where can I go to find it? So the first one was we just did tokenization. We didn't do any other fancy backends. You don't need SPASI, you don't need Java, you don't need Python, you just need the tokenizer's backend. It's pretty easy to set up. And although you can do an approximate job of essentially any natural language, so you can do Farsi or Chinese or Navajo or essentially anything by just setting the correct locale. But then we moved on and showed how if we're using a language like English or French or Spanish or Arabic, where there are specific models written for them, we can learn a lot more about the text. So we can get part of speech codes, we can get named entities, we can get dependencies. We just started showing why those are useful. So in some sense, they just do a more accurate job of what we did with the tokens. In other sense, they can really extend them, like doing document summarization, things that we couldn't do with just the tokenized text. And then the last bit, we wanted to show how we can take what comes out of the clean NLP package and apply it to sort of just generic modeling, but also text-specific models like topic modeling. So there are a lot of other R packages. If you go to the natural language processing CRAN working group page that has all the packages, a lot of them, a large chunk of them just accept a matrix, so you can plug them into what comes out of this and use them. But what we found is nice, so what you've noticed is that while we were using the topic models package, we didn't just give it the term frequencies, like an analysis that didn't use the clean NLP package, we gave it just the nouns. And while giving it all the words or just removing stop words is okay, filtering out just the nouns actually gives better results, or results that to us look more interesting. So there we go. So the things we didn't cover, we started preparing this talk with an outline that was like 10 times longer than it could ever possibly have been. So these are just things that we didn't get a chance to talk about, but happy to talk about them afterwards or point you in the right direction. So we didn't talk about pre-processing data. So as I think an early question asked, so we assumed that you have come to us with the clean text in some file or in memory. So we didn't talk about getting rid of HTML tags or getting rid of misspelled words or diacritics or things that are wrong with the text. So we just assume everything's okay. That's an important step, and it's a pre-processing step before you get to the annotation process. We didn't talk about 2 annotators or 3 annotators, so sentiment analysis that tells me whether or not a sentence is happy or sad, and then there are other sentiments that can tell you whether or not something is sarcastic or sardonic or miserly, or there are different sentiment approaches. One of them is contained in the Core NLP package, or in the Core NLP backend, and one is in the SPASI backend, but we didn't have a chance to talk about that. I think you have to be careful with them too, because unless you're using it on a very specific corpus, I find the results that come out of the sentiment analysis can be a bit noisy. And then co-references find links. They're like dependencies, but they're links between words in different sentences. So if I said, Lauren enjoyed coming to useR, she had a great time, Lauren in the first sentence and she in the second sentence would have a co-reference to one another because they're referring to the same entity, but they're in different sentences, so they don't have a dependency. So co-reference is one of those cutting-edge things that's only in the Java library. I think in 3 or 4 years it's going to be fantastic. It's a bit buggy at the moment. And then the last one that we didn't cover that is offered in the clean NLP package are word embeddings. So this is a pre-learned mapping of words into a 300-dimensional space. And so it's a different way of going from words to matrices. And it would just, if we had another topic that we would do, I would probably do word embeddings, but it's just a huge thing and we didn't have time to go into it. The non-Western languages, like we talked about them actually quite a bit, but we didn't show an example of them. And then the other thing that you can do with clean NLP that Lauren and I have been working on a project recently that involved doing this was to reconstruct the original text. So we've parsed the text, we've learned things about it. Sometimes we actually want to then reconstruct the text. So what's an example of why this might be useful? Well, say we are teaching Sherlock Holmes in a class, so we have an algorithm that detects all the main characters, figures out where they are. One thing we could do is we could make an HTML page out of that that highlights all the times Sherlock Holmes or John Watson are mentioned. Right? You can think of adding some tags in there and using some base R functions to do that. We can do that with the addition of that spaces column that I sort of glossed over at the beginning that tells me how much additional white space has to go everywhere to reconstruct the original text. And then the other thing that's just sort of really opens the Pandora's box of all the things we can do are that we've only looked at a few of the part-of-speech codes. I think you can do something interesting with almost any of them. We've only looked at 2 of the dependency types. There are 40 of them. They're all fascinating. I think you can, I don't think enough statisticians have looked at them and really figured out all the interesting modeling things you can do with dependency tags. I've looked at the direct objects for summarization and the noun for doing compound words, but there are so many others, and I think there's a lot of potential there for what you can do with them. And then the last one are the entity types. So we just looked at the location, or the people essentially. One thing that's neat that we've looked at is using the location tags and using a geolocation service to link the mentions of locations in the text with latitude and longitude, and then you can build maps, like a map of a Twitter feed that sort of shows where like CNN and Le Monde and BBC are talking about at any given time. So you have like a little app that does that in the background by doing the named entity recognition, looking them up and plotting them. So there's a lot you can do with these things, and I think we've looked at a few others that we haven't shown today, but I think there are a lot more that we haven't even found. So there's a lot of exploration there that we haven't done. And then just some other references. We mentioned a few of these before. There's the Clean NLP package if you just look up, or there's the Clean NLP paper. If you find the package on CRAN, there's a link to it, or if you go to the GitHub page, there are links all over the place because I want everyone to read it. There's our book, The Humanities Data in R, which we'll talk about in just a second. We have a pedagogical paper, Basic Text Processing in R. So if you're an academic and you want to maybe teach this material, but you think what we've covered today is maybe a bit too much to teach, maybe like in an intro undergrad class, this article here boils this down to sort of the really quick salient points. It just uses the tokenizer's backend. It looks at the State of the Union addresses, and it does some interesting things without having to get too deep into all the natural language processing tasks. And then, of course, I'll be giving a talk tomorrow that goes into more of the internal structure of Clean NLP, so not so much how to use it, but why it's built the way that it's built. And then Lauren has one thing about the book.
If you want a free copy, we're going to do a little raffle, so you just have to come up here during the Q&A and put your name in if you would like a free copy. So,
Yes.
And we'll tweet a discount link to you. And we're going to tweet out the slide deck and all of that
Yes.
After this talk as well, the links to all the components here as well, so that you can have them as well. We weren't able particularly to connect today with the internet.
Yeah, I'll put that up there too.
So I think with that.
So I think with that, we can do some questions. So any other questions? Uh-huh. Oh yeah, that's a good point. So we weren't looking at the bigrams and trigrams, but that's kind of the next step to look at them. What's actually interesting about so bigrams and trigrams are just looking at pairs of words or triples of words is that once you have the fully parsed text, you're not stuck with just putting words that are next to one another. You can look at bigram, like dependency bigrams. So you can look at all the words that are connected by a dependency, which is actually much more interesting because you see the actual noun that's attached to the verb. You see the actual adjectives that are attached to the nouns. And so we have looked at that, but we were just sort of keeping it simple. But yeah, that's kind of the next step of this. And the bigrams really help, the dependencies really help make sense of those bigrams and trigrams. So yeah, but yeah, you can definitely do that to get more. We were looking at themes, so that wouldn't help so much, but if you wanted to look more at style or like rhetoric, real rhetoric, like how are they using the language, that would be what you'd want to go after, would be the bigrams. Uh-huh.
So what do you do when you have your principal component analysis and then you have, I don't know, 30% of principal component 1 and maybe 17 of principal component 2, and there's so much variance that is not explained by the TCA that you have done, and you don't want to show principal component 3 versus principal component 8, which is basically 99% of all variance. How do you justify that you have explained only less than 50% of variance? How do you do that?
Oh yeah, so if I ran into the case where I had a principal component analysis and it, the first few components didn't explain much of the variance or, collectively didn't, what I'd try to look at would be to do some nonlinear dimensionality reduction like t-SNE to see if that would do a better job of it. So because if I can't capture it in 2 dimensions very well at all, there's probably some nonlinearities. So PC is a linear dimensionality reduction, so I'd look for something that's nonlinear, like a t-SNE, so that does a different form of dimensionality regression. So you can think of PCA as like a plane, t-SNE is like a blanket, so it can do a better job of doing it. So I found most times that fixes the problem, so you can get most of the variance in that t-SNE space. But yeah, it's a good question. Mm-hmm. Mm-hmm. So how would we do topic modeling if we had multiple languages all at the same time? So one thing to do is you could just construct the term frequency matrix, the bilingual term frequency matrix, and ignore the fact that we have words in this that meaning the same thing but in different languages. In some sense that would be okay because in English we have synonyms of words and we have 2 columns for those and we're not collapsing them onto one another. The other option, if you really wanted to still do topic modeling in the topic modeling framework, is you could use one of the many different ways of doing translation. So for nouns, that would work pretty well, actually, to do translation into another corpus. The other thing that you could do that I've actually been experimenting with is bilingual word embedding. So we were describing the term frequency matrix, which is kind of the classical way of going from the tokenized text into a matrix. So word embeddings is a different way of doing that. So it's just, there's a fixed mapping from every word into a large dimensional space. So bilingual word embeddings actually say, okay, I'm going to have a Dutch space and a French space and an English space, and I'm going to rotate them all so that the word apple is close to the French word for apple and the German word and the Dutch word. And so in that space, everything would make sense. So those would be the 3 different. So just ignore that they're different languages, try to translate them, or actually do the word embeddings, which lets you play in a space where all the languages have been normalized into the same high dimensional space. So yeah, so any other questions? Oh, British and English? I haven't dealt with it myself, but the corpora that I know of, I haven't had any problems using something that's trained on the British National Corpus, which is one of the biggest training sets of British English, or on the Penn Tree Bank one, which is American English, and I've used one to tokenize the other, and like the British National Corpus models to do English text and vice versa, so I don't think that it would be a problem. I think that they are generic enough to be quite okay, those 2 versions of English. If you had a really dialectic language like Italian or something, which has, where you can really get quite different, then that might become a problem, where you get the problem in English of like Twitter English versus newspaper English. But formal British English and formal American English doesn't seem to be a problem. They're robust enough to capture that. If that was your question, right? Okay. Uh-huh.
We take unstructured data and put constraints on it based on your understanding of the language and the structure of the language, and change unstructured data into a structured format that you can analyze using algorithms and so on.
Mm-hmm.
That may be a very simple understanding of the approach to NLP, but at least that's what I saw in your presentation so far. Is it possible for two different research teams to take a look at the same data set, come up with different constraints based on their own understanding, and come up with different interpretations of the same data set? If that is so, what does this mean for replication from a philosophical science point of view?
Okay, so it's definitely possible that, like, even just within clean NLP, you could use the core NLP backend, or you could use the SPASI backend. So in the paper actually has an example of a sentence where the word yell can be a noun or it can be a verb. And in the sentence, it's actually a verb, but SPASI correctly determines that it's a verb. Core NLP thinks it's a noun. So even within the package, there's an inconsistency between what you're doing. So, I mean, for replication from a science perspective, that's fine. You just have to say what model and assumptions you used. I think that's true of any scientific analysis. The idea of taking the unstructured and structuring it, that is the whole idea of this. You're absolutely right. So I said at the beginning, I work with text and images. So we've been talking about text. So text, structuring text, you are taking unstructured data and structuring it. There's a little bit of a difference there because what we're doing is actually non-destructive. So like we were actually saying, one thing you can do with the data frame is you can reconstruct the original text. So going from the unstructured to the structured, I have not actually lost anything. When I work with images, it's very different. So if I take an image and I do a neural network embedding, like VGG type models, like if you're familiar with that structuring, image is very different because the embeddings that I get and the kind of tidying of that data that I get, you cannot reconstruct the image from it. So text kind of sits in this liminal state. It's unstructured in the sense that it's not a nice data frame. I need to do stuff to it to structure it. But I'm not destroying anything about the text. I have all the original words. I have all the white space. I can reconstruct the text. So it's true that the models that I'm using to extract some of the features are learned, and they're subject to opinion and whatever your corpus is. So you should always be cognizant of that and say what you're using. So I would think that if somebody wanted to write a paper about this, ideally in the method section, you would say, I'm using clean NLP and I'm using SPASI, and I'm using this specific SPASI. I'm using the English newspaper corpus version 1.2, so that it's fully reconstructed. But I think keeping that in mind is an important thing, that it's different than getting rid of all the missing values, right? Like I can just put that in my code. It may be lost in the code what version of the model. So yeah, but that's a good point. Do we have time for a couple more questions? Uh-huh.
When you classify words into location, piece of art, and so on, how do the words fall into multiple categories?
So the figuring out, which category it's in. So that's actually done by the underlying model, the SPASI or Core NLP model. So I'm not actually doing that. It's figuring it out. The way that these were done is that people went through and hand-tagged texts. And they said, this is a location, this is a person, this is a work of art. I think the categories are, while in general something could be multiple things, I think most of the categories are fairly exclusive in context. So when you read the sentence, it's obvious that Australia is being used as a location or a political entity like that. I don't know, it would actually go back to, when you really do have to choose, it would just go back to how they were tagged. I can give you a little bit of information about how the model is figuring out whether or not something's a work of art or a person or a place. So it's doing two things. One, it has a list of words that it knows are people and places and things. When it doesn't know that, it has rules like capitalization where it can figure out that something's a proper noun, and then it uses hints like what verbs is it attached to. So we know that if I'm going to something or if I live somewhere, that the next word that's attached to those words that refer to location is a location. If something says if something looked like a proper noun and it says something, the verb says is attached. There's attached to agency, and so we assume that that's a person. So there are these two. There's one, we just have a bank of all the words, and then when that fails, it uses the verbs or adjectives that are attached to it. But in the case of tagging the original text that it was learned on, when there's two categories, I'm not sure. But I think most of the ones where they would overlap, in context, there's one application. It's just, it could be multiple in different contexts.